Good morning, statistics students. Today we're going to do more with the binomial distribution. On Monday you were working with a problem where you were calculating binomial distribution sort of by hand, kind of using the logic of how this works. I sent you a sheet that shows you the correct answers for the problems I assigned. Please check your answers because some of you didn't get the right answers. So the sheet I sent you looks like this. It was page 2, the one you had to do x equals 3. That one comes out if you follow through it all. 0.0154. Here's all the math. And then the other three, the three at the bottom of the page, these three, I did on a separate page just to show you how to work. Some of you guys saw how to do it and you wrote down the quick calculation, that's fine. But this is the logic of it. All of the problems have n equal 4. There's 4 trials or 4 repeats of rolling the die. The underlying probability of success and failure for this problem is still 1 in 6 because we're interested in the success being getting a 6. Failure is not getting a 6. And then here are the ways you can do 0 successes, 2 successes, or 4 successes, and the probability calculations to figure out the odds of each of those happening. So I'm not going to dwell on that. You can compare your own. You might refer to that during today's lesson, though. So anyway, today we're going to formalize the binomial distribution probability calculation into a formula. It's going to look a little unusual, the formula, but what you did for homework is basically the formula. We're just going to, I'm going to explain the notation in the formula. The first thing you need to know is what a factorial is. These factorials are used a lot in math. If you ever take calculus, there's times they're used there. There's sequences and series use factorials, which are a branch of math, and probability uses them. So this is the definition. N is a positive integer, then n factorial is defined this way. N, this exclamation point, when you see it after a number in math, it means n factorial or 5 factorial, whatever the number is. And it means take that number and multiply it by every number going down by 1, every integer going down by 1 all the way down to 1. There's a special case when n is 0. 0 factorial is defined to be 1. We don't have a definition for negative numbers factorials. They don't come up in math in the way that the positive integers do. So this is our definition. So here's 2 examples of just using a factorial notation correctly. If I said evaluate 5 factorial, that really means, according to the definition, 5 times 4 times 3 times 2 times 1. If you do that out, it comes out 120. And I want to show you a shorthand thing with this next example. 6 factorial, you could write that as 6 times 4 times 3 times 2 times 1. But I could also think of that as 6 times 5 factorial, because remember 5 factorial means 5 times 4 times 3 times 2 times 1. And since I already did the work to figure out 5 factorial, I know that equals 120. So it's 6 times 120, which is 720. So this is just, sometimes it's useful to think of a factorial as another factorial multiplied by the extra numbers you need. Why are we learning this? Because of this definition. The binomial coefficient is the number of ways of arranging k successes among n observations or trials. Observations means trials, but this is the book's definition. So they go back and forth between observations and trials, but either word means you're repeating a chance process over and over, where the outcomes are either success of whatever you have defined as a success and failure, which is everything that's not a success. So, and it's given by this binomial coefficient. This reads, this is the number of ways to have k successes with n trials or observations. So n is this is n, this is k. And it's n factorial using this definition over k factorial times n minus k factorial. And k could be any number from 0 to n, because you can have any number of successes up to the number of trials. So you can't have k bigger than n because you can't have, say, in our rolling of a dice example, we rolled the die 4 times. You can't have the outcome get a 6 5 times because we only rolled the die 4 times. Now, if I rolled the die more times, then you could get a 5. But for our definition of x, which was the number of 6s you get when you roll a die 4 times, the largest number of successes you can get is n, which is 4. So that's what that's saying. So let's look at actually our example, our dice rolling example. Same example you worked on Monday. If I roll a dice, 6-sided die 4 times and is 4, how many times can I get 6? Can I get a 6 2 times out of the 4 rolls? Maybe make this rolls to be more clear. Well, you guys actually know that if you did your math work right on for your homework. This is the situation. We want 2 successes, 2 6s to come up out of our 4 rolls. And these are the different ways of doing it. We know it's 6 from writing them out. This formula will calculate that it's 6 correctly. So let's do it out. Our n is 4. The number of successes we're interested in is 2. So it's 4 factorial over k factorial, which is 2 factorial, over the difference of 4 minus 2 factorial. This 4 minus 2 becomes this 2. So you have 4 factorial over 2 factorial times 2 factorial. Writing these out, this means 4 times 3 times 2 times 1 over 2 times 1, which is 2 factorial, times 2 times 1. If you do the math, this whole fraction becomes 24 over 4, which is 6. We already know it's 6. We wrote out the 6 ways you can get 2 successes and 2 failures on 4 trials, and it's right here. That was part of your homework. P of x equals 2. So you could, with small number of trials, you can often figure out the number of ways to get a certain number of successes, but this formula is very useful when you have a large number of trials and it's very hard to write down all the possible combinations of success and failure that you're interested in. So this formula will always give you that count. In this table down here, we're taking what you did for homework and using the binomial coefficient to show you these counts. These are the possible, same problem, 6-sided die, 4 times we're rolling it. We want x to be the number of times you get a 6, just like you had on your homework. Fill in this chart. N is still 4 repeats of the roll. Probability of a success is 1 in 6. Probability of failure is 5 in 6. So k can be any value up till n. So it's 0, it could be no successes, 1 success. These are the 5 probabilities we did in class and for homework last time. Here it is calculating the binomial coefficient using the formula right here. I put in 4 for n in the numerator in all of these. The denominator, this first factorial is k factorial. The second one is the n minus k factorial over and over. And simplifying the parentheses, you get 4, 3, 2, 1, and so on. These 2 numbers should always add up to n, by the way, because you're saying what it really is telling you is the number of successes and the number of failures. So anyway, doing the math on these, you get 1, 4, 6, 4, 1. That is the number of ways to get these different outcomes that we did on Monday. There were, like the first problem we did in class on the video I showed you Monday was this example, x equals 1, and we had 4 ways of that happening. So that's what that is. Here's the, now I'm saying calculate the probability that x equals this k. These are the probabilities we did Monday. So it's like one way to do this times the probability of failure, 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 failure. That comes out 0.4823. That's your homework problem, and so on. I'm going to let you look at that for a minute to make sure your answers are right. These are what you did for homework. And each of these is a probability that x equals one of these numbers. So what you're doing is saying, if I want 3 successes, I have 3, this is success, 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 failure. Now these could be arranged differently. There's 4 ways to arrange this, but you don't need to keep doing, oh, success, failure, fail, success, success, and so on. You have 4 ways of doing the same calculation. So those add up to 0.999997. They don't add up to 1 because of rounding, but these probabilities should add up to 1 or close to 1, because these are the only possible values of x. This is our complete sample space as x is defined, which is the number of ways you can get a 6 in 4 rolls of a 6-sided die. Okay? Now, all of this is really leading to this next formula. This is the binomial probability formula. This will always work to calculate the probabilities of a binomial distribution for a certain outcome for the variable x. You did this actually on your homework, you just didn't know it was a version of the formula. So what it's saying is this is the binomial coefficient. It represents the number of ways to get k successes. That's what that is. That is the number of ways to get k successes. That's the binomial coefficient. And then this part is the probability of success, which is p, raised to the k power. So if you wanted 3 successes, it would be success, the odds of success multiplied by itself 3 times the probability of failure multiplied by itself the remaining number of times. So that's n minus the number of successes you're interested in. Let's do an example to see how this works. This is a dice example, but it's different than the one you did for homework. We're going to say we have a 4-sided die, and we're going to roll it 5 times in a row. We're going to calculate the probability that you get a 3 2 times. So success is get a 3 on a roll. Our variable x is the number of 3s you get when rolling a 4-sided die 5 times. It's good to lay these things out before you get started to make sure you understand what your variable x is and what you're going to call a success. Our number of trials is 5. I've underlined that in green. That's how many times you're repeating your chance process. The number of times we're interested in calculating a probability is of 2. Okay, we're interested in how many times, what's the probability of getting a 3 2 times. Our underlying probability of success is 1 in 4 because it's a 4-sided die. Therefore, the probability of failure is 3 in 4. Here is plugging into the formula up above using these numbers. I hope you can see that. And then I worked out the math. I'm not going to explain it all. You can stop the video and copy this down if you want. Actually, you should. But the final probability comes out about 26%, or 0.2637. So that's one comment here, though. When I'm doing this factorial here, this is 5 factorial over 2 factorial times 3 factorial. This is our count of how many ways you can have 2 successes out of 5 trials. I wrote 5 factorial as 5 times 4 times 3 factorial, and then I reduced that 3 factorial out. You can multiply this all out and divide it with your calculator, but if you can also reduce along the way. That's up to you. Sometimes you get some fairly large numbers, so reducing along the way keeps the numbers under control so your calculator doesn't go to scientific notation on you, which can be a pain. This next problem, if you want to try it without listening to the video, go for it, and then you can check your answer. Here is the answer, and it's showing you the number of ways to get 3 questions correct on a 6-question multiple choice test with 4, make this correction here, with 4 possible answers, A, B, C, or D. You're going to guess on each question what are the odds you get 3 correct. That's basically getting a 50%. So I've identified X. It's the number of questions you get correct on a 6-question multiple choice test. I could even say with 4 possible answers on each, because if you had 5 possible answers, the probabilities would change. On each question, I should say. Sorry, on each question. Sorry, it's messy. And then N is 6, because there's 6 questions on the test. We're interested in getting 3 successes. Our probability of success on any one question is 1 in 4, and therefore the probability of failure on any one question is 3 in 4. Unlike this problem here, I'm going to find the number of ways to get 3 successes with 6 trials first, because this calculation kind of is cumbersome, and just get it out of the way and we'll plug it in. So it's 6 trials with 3 successes. The formula says this. Simplifying, I get 20. That means there's 20 different arrangements of 3 successes on a 6-question test that you could have. You could randomly come up with. We're going to plug that number into our formula here, but then the probability is going to use this big formula that we want our variable x to equal 3 successes. So it's 6 trials with 3 successes. The probability of success is 1 in 4, that's raised to the 3. Probability of failure is 3 in 4, that's raised to the 3, because that's n minus 3, 6 minus 3. This 20 I'm taking from here, I just did this calculation beforehand. And then this is 1 in 64, 1/4 times 1/4 times 1/4 is 1 in 64. 3/4 cubed is 27/64. That whole fraction, that multiplying, this is 20 over 1, don't forget. So it's 20 times 27 is the 540. 64 times 64 is 4096. Dividing that on your calculator, you get 1.1318. What that means in words, this is important, because you might have to put things in words. There's a 13% chance of getting 3 out of 6, or 50% correct, on a 6-question multiple choice test where each question has 4 possible answers. That's not good odds, right? Hopefully that's an incentive to not guess, to come to tests and quizzes prepared, because obviously if you leave it to chance, your odds of getting just a 50 on a test, a 6-question multiple choice test, is a mere 13%. So your homework's to try these 2 problems, which are similar to these. They're binomial situations where you have to calculate a probability of a certain number of successes. So using this formula. That's it. Thanks for listening.